Where aerodrome pavements, runways, taxiways and aprons are used by aircraft with weights of more than 5,700 kilograms, the strength of the hard surfaces are reported by using a pavement classification system. This system is essentially a published 5-part code, which reports on the type of surface at the aerodrome and its load-bearing strength. The important part of the pavement classification system is the first section, the load-bearing strength of the particular surface, simply referred to as the pavement classification number, as shown here. This value must be compared to the load force of a manoeuvring aircraft. This load force is portrayed as the aircraft classification number, ACN. It is a unique number expressing the relative load effect of an aircraft to a surface type and thickness. Generally speaking, the aircraft classification number must not exceed the pavement classification number for the same surface. Otherwise, the surface will deteriorate quicker than its design life. For example, an aircraft with a classification number of 110 on a particular surface type should not manoeuvre on a pavement with a classification number of 35 on the same surface type. Chances are the aircraft would seriously damage the surface and most probably embed itself. When pavements are designed for use by aircraft with a ramp mass of 5,700 kilograms or less, bearing strength is reported in terms of the maximum mass allowable and the maximum tire pressure allowable. Information on the condition of the movement area of an aerodrome and the operational status of the facilities related to it must be provided to the appropriate Aeronautical Information Service units. To enable arriving and departing aircraft to have the most up-to-date operationally significant information, it should also be available to air traffic service units. The condition of the movement area and its associated facilities must be regularly monitored, and matters of significance reported on without delay. This is particularly the case in respect of construction and maintenance work, rough or broken paved surfaces, snow, slush or ice on runways, taxiways and aprons, water on runways, taxiways and aprons, snow banks and drifts adjacent to runways, taxiways and aprons, anti-icing or de-icing liquid chemicals on a runway or a taxiway, temporary hazards, including parked aircraft, failure or irregular operation of part or all of the aerodrome's visual aids, and failure of the normal or secondary power. Runways are the part of an aerodrome's manoeuvring area that is used for takeoff and landing of aircraft. With few exceptions, runways are prepared and usually made of concrete or tarmac. Runways are straight and do not have excessive slopes. Usually both ends can be used for takeoff or landing, and in all cases, runway markings painted on the surface will provide the pilot with indications about the use of the runway and assist him in landing. It is normal practice to take off and land into wind. Several factors influence the runways on an aerodrome. The most influential is the wind, and it is this that controls the alignment and number of the runways built. The number of runways should be such that the usability of the aerodrome is not less than 95% for the aeroplanes that the aerodrome is intended to cater for. Runways are largely defined by their use, rather than their physical characteristics. An airfield, a grass area upon which runways may be marked, may have several or no defined runways, whereas an airport, a point of country entry, may have several defined and paved runways of the very latest design and specification. It is the types of operations carried out on a runway that determine the runway type. The service provided, markings, signs and physical characteristics are all type dependent. A non-instrument runway is one where takeoffs and landings are undertaken visually. These operations are usually defined by reference to ground visibility, or runway visual range, cloud sealing and daylight considerations. The runway markings will reflect this type of use. An instrument runway is one to which instrument departures and approaches are made using defined procedures. Departing aircraft will utilize the procedure in the form of a standard instrument departure, and arriving aircraft will use runways subdivided into precision runways, using ILS, GLS, MLS or PAR approaches, non-precision approaches, using VOR, NDB, SRA or ILS azimuth-only approaches. A takeoff runway is one that can only be used for takeoffs. This is usually because of terrain constraints, preventing approaches or missed approaches. The threshold of a runway should normally be located at the extremity of a runway, unless it will be operationally prudent to do otherwise. If the threshold is displaced, then the runway will be marked as shown here. The length of a runway should be adequate to meet the operational requirements of the aircraft that are intending to use the aerodrome. It should not be less than the longest length calculated to correct for local conditions of elevation, temperature, slope, humidity and surface characteristics. There is no requirement to cater for the worst-case critical aeroplane at maximum mass. Runway length is reported in meters. However, fixed distance markers are placed along the edge of the runway 1,000 feet apart, starting 300 meters from the threshold. For a paved runway to accommodate instrument approaches from either end, it must be at least 1,800 meters between thresholds. The width of runways is also important, and clearly should be suitable for use by all the aircraft that intend to use the facility. The primary factors deciding the width of a runway are wingspan and outer main gear wheel span. Widths of runways can be specified in terms of the Aerodrome reference code, as shown here. The shoulder of a runway is the area adjacent to the edge of a paved surface, so prepared to provide a transition between the pavement and the adjacent surface for aircraft running off the pavement. Shoulders are recommended for all Code D and E runways with a width of less than 60 meters, and for all Code F runways. The overall width of the runway and its shoulders should not be less than 60 meters wide for all D and E coded runways, and 75 meters for Code F runways. The perception that most people have of an airfield is that there is simply a runway of a certain length which is used for takeoff and landing. The truth is that a runway is too broad a term to describe the various takeoff and landing portions. There are, in fact, 4 uniquely declared lengths on any runway, and 2 unique runway extensions. We will deal with the runway extensions first. For commercial and operational reasons, there may be an extension to the runway called a stopway. A stopway is a defined rectangular area beyond the end of the takeoff run available, which is defined later, in the direction of takeoff, no less wide than the runway and centered upon the extended centerline of the runway. Stopways cannot be used for any purpose other than bringing an aeroplane to a stop after an aborted takeoff. Therefore, they cannot form part of the landing or takeoff surface. To help the pilot recognize the stopway, it should be distinctly marked with yellow chevrons, as shown here. Other than a stopway, there is one other additional type of extension that can be made to a runway. This is called a clearway. A clearway is a defined rectangular area beyond the end of the takeoff run available, not less than 150 meters wide, centrally located about the extended centerline of the runway and under the control of the airport authorities. The clearway is actually the area underneath the clearway plane. The clearway plane extends from the end of the runway with an upward slope not exceeding 1.25%, above which no object or terrain protrudes. The length of a clearway will be the lesser of the following 2 distances. The distance to the first upstanding non-frangible obstacle, or frangible objects of 0.9 meters or more in height, or a distance equivalent to 50% of the takeoff run available, which is distance that we will define shortly. Having dealt with the two types of runway extensions, let's now focus on the four specific operational distances at an aerodrome. These are takeoff run available, TORA, takeoff distance available, TODA, accelerate stop distance available, ASDA, and the landing distance available, LDA. The first of these distances to consider is the takeoff run available. It is defined as the declared length of runway, starting at the point from which an aeroplane can commence the takeoff and ending at the nearest point which is unsuitable to bear the load of the aeroplane under normal conditions. Information about the takeoff run available will be published in aerodrome charts, like the one shown here, but temporary changes in takeoff run available length, because of maintenance or work in progress, would be published in the NOTAMs. Always consult the NOTAMs so that you are kept up to date about the latest changes to the aerodrome conditions, or to the airspace in which you operate. The second of the specific distances that a pilot needs to understand is the takeoff distance available. The takeoff distance available is that distance from the point on the runway at which the aeroplane can commence its takeoff run to the nearest obstacle in the direction of takeoff projecting above the surface of the aerodrome and capable of affecting the safety of the aeroplane. At most aerodromes, the takeoff distance available will be the same length as the takeoff run available, as illustrated here. This is the concept of the balance field that you will meet in your studies of aircraft performance. However, if there is a clearway present, the takeoff distance available can be increased beyond the takeoff run available to include the clearway. You may recall that there was a maximum permissible length of clearway which equated to 50% of the takeoff run available. In simple terms, the takeoff distance available is the takeoff run available plus the clearway, if a clearway is present. The third of the specific distances at an airfield is the accelerate stop distance available, or ASDA. The accelerate stop distance available is the distance from that point on the runway at which the aeroplane can commence its takeoff run to the nearest point in the direction of takeoff, after which the aeroplane cannot be brought to rest in an emergency without the risk of accident. At most aerodromes, the accelerate stop distance available will be the same length as the takeoff run available, as illustrated here. However, if there is a stopway present, the accelerate stop distance available can be increased beyond the takeoff run available to include the stopway. Remember though, the accelerate stop distance available is to be used solely for the rejected takeoff. In simple terms then, the accelerate stop distance available is equal to the length of takeoff run available plus the stopway, if a stopway is present. The last of the specific distances we need to mention is the landing distance available, or LDA. The landing distance available is the length of the runway which is declared available by the appropriate authority, commencing from the point on the surface of the aerodrome above which the aeroplane can commence its landing run, and extending to the nearest point in the direction of landing beyond which the surface of the aerodrome is incapable of bearing the weight of the aeroplane under normal operating conditions. The length of the landing distance available is easily identified by the distance between the thresholds. There is no other distance that is allowed to be used for landing. Even stopways are not permitted to be used. A runway strip is defined as a surrounding area, including the runway, and stopway if one exists, in which obstacles are kept to a minimum. Any obstacles that are operationally necessary, lights, equipment cabins, etc., must be frangible. The purpose of a runway strip is to reduce the risk of damage to aircraft running off the runway, and to protect aircraft flying over it during takeoff or landing operations. The dimensions of a runway strip should extend before the threshold and beyond the end of the runway or stopway, for a distance of at least those defined here. 60 metres where the runway code number is 2, 3 or 4, 60 metres for a Code 1 instrument runway, and 30 metres for a Code 1 non-instrument runway. The width of the runway strips are to extend, when practicable, laterally on each side of the centre line of the runway and its extended centre line, through the length of the runway strip to a distance as defined here. Code 3 or 4 instrument runways shall have an area 75 metres either side of the centre line, graded so that aeroplanes which the runway is intended to serve shall have an area that they can safely run off the paved surface onto in the event of an emergency. For runways coded 1 or 2, then the distance will be 40 metres. No fixed object other than visual aids are permitted on a runway strip within 77.5 metres of the centre line for Code 4F, Cat 1, 2 or 3 runways, or 60 metres for Code 3 or 4 Precision, Cat 1, 2 or 3 runways, or 45 metres for Code 1 or 2, Cat 1 runways. No mobile objects are allowed within the runway strip during takeoffs or landings. The Runway End Safety Area, RESA, is an area of land usually at each end of a paved runway, either side of the extended centre line, that does not form part of the operational runway. It will be free from obstruction and is set aside in case an aeroplane overruns the end of the runway. It will be at least twice the width of the runway and extend for a distance of not less than 90 metres from the end of the runway strip. RESAs will be provided for all Code 3 and 4 runways and for Code 1 and 2 instrument runways. The radio altimeter operating area is established in the pre-threshold area of a precision approach runway. Don't forget that for Cat 2 or 3 operations, the use of rad-alt is mandatory to determine DH. Thus the area should extend laterally on each side of the extended centre line of the runway to a distance of 60 metres, and for at least 300 metres from the end of the runway. It should be as level as possible. Taxiways at aerodromes are designed to expedite the movement of aeroplanes to and from the runway and include the areas provided as fast turn-off lanes from main runways where traffic volume is high. Where the end of a runway is not served by a taxiway, then an area large enough for turning is to be provided. Taxiways may cross, join and intersect each other. At major aerodromes, they will require signs and markings to enable pilots to reach their destinations, often a confusing task. They must also be readily identifiable. Some taxiways run parallel to runways and must therefore not be confused with the landing surface at all. Consideration must also be given to the places on taxiways where aircraft hold, prior to entering a runway for takeoff, for example. The large mass of an aeroplane may also interfere with ILS or MLS systems if parked in front of them, or be a significant obstacle to landing aircraft if parked too close to the threshold. In general terms, however, taxiways should, according to Annex 14 of the ICAO regulation, provide safe and expeditious movement of surface movement of traffic. A major limitation to an aerodrome would be the capacity of its taxiways to accommodate different sizes of aircraft. Their load-carrying ability and width are major influencing factors in the capacity of an aerodrome to operate efficiently. The strength of a taxiway must be at least equal to that of the runway. Given the stopping, turning, loading and unloading taking place on them, they are more prone to damage than runways. Width is the most important factor to consider when designing taxiways, and the table shown here shows the minimum requirements for clearance of the outermost main wheels when the nose wheel is on the centre line of the taxiway. The straight portion of a taxiway should have a width of not less than that specified in the table shown here. Any changes in direction of a taxiway should be few and gentle in nature. The radii of the curves should be compatible with the manoeuvring capability and normal taxiing speeds of the aeroplanes for which the taxiway is designed for. Corners may well have to be widened to accommodate large aircraft. Taxiways are required to have a painted centre line which should be illuminated at night. Pilots must keep the nose wheel of their aircraft on the centre line, especially during turns, as this will ensure that the main wheels keep on the taxiway. To expedite aircraft movements, at larger aerodromes, aircraft are allowed to turn off runways at higher speeds and on lanes that do not turn through sharp angles, using rapid exit taxiways, or fast turn-off lanes as they are called. They are located along runways and are designed and constructed to cater for turn-off speeds of 50 knots for code 3 or 4 runways and 35 knots on code 1 or 2 runways in wet conditions. The area is to include a straight section after the initial turn-off curve to allow an exiting aircraft to come to a full stop clear of the intersecting taxiway. The intersecting angle with the runway should not be greater than 45 degrees or less than 25 degrees, preferably 30 degrees. The shoulders of a taxiway, used by turbine-powered aircraft, are to be prepared in such a manner that they prevent erosion by jet blast, which can cause the ingestion of surface material into aircraft engines. Taxiway strips, similar to runway strips, are provided to delineate the area to be cleared of objects which may be obstacles. Busy aerodromes nearly always have a backlog of aircraft waiting to take off, so it is essential that any such queue does not exceed the capacity of the taxiway to accommodate all the waiting aircraft. In this situation, or where environmental considerations exist, holding bays are provided adjacent to runway entrances, designed to leave taxiways clear. Regardless of the position of holding bays, the entrance to a runway will be protected by a defined mandatory holding point, set back from the edge of the runway to accommodate all traffic. It will be in such a position so as not to impinge upon the obstacle limitation surface, or interfere with the operation of radio navigation aids, like the ILS or MLS. We will show you the signs and markings associated with the holding position later on. The final consideration when looking at taxiways is that of vehicular integration. A road holding position is a designated place at which vehicles may be required to stop and wait, where taxiways are used as roads for vehicular traffic. The distance away from a runway centerline for such a hold is the same as that for aircraft holding positions. Normally there will be traffic lights at this vehicular hold. The apron is the area of an aerodrome that permits the embarking and disembarking of passengers, cargo and mail, as well as allowing an area for the basic servicing of aircraft, without interfering with the day-to-day aerodrome traffic. The total apron area should be capable of allowing the expeditious handling of the aerodrome traffic at its maximum anticipated density. Aprons must be built to accommodate slow-moving traffic and be stronger than the other areas of the taxiways and runways. Aircraft parking areas, or stands, are to be clearly marked and are required to provide a minimum distance between parked aircraft. All commercial aerodromes must have a designated, isolated aircraft parking position that can be used to park an aircraft that is known or believed to have been subject to unlawful interference, or which for any other reason needs to be isolated from the normal day-to-day aerodrome traffic. This area must be at least 100 metres from any other parking area, building and public area, or over or underground utility service. Now let us move to the subject of runway contamination, which in this case means water in its various forms lying on the surface of the runway. These forms are frozen water, that is ice and snow, melting snow, that is slush, which can also be formed by a mixture of rain and snow, and liquid water. Just as we remember the problems of our first attempt at ice skating, so aircraft may suffer issues of directional control and, of course, stopping. Whenever the runway is contaminated by frozen or partially frozen water, ICAO recommends that for each third of the affected surface, a measurement of depth is carried out. The depth of dry snow should be assessed to an accuracy of 2 centimeters, wet snow to 1, and slush to 0.3 centimeters. As you can see from the measurement requirements, snow has its different states: dry, wet, slush, and compacted. Their definitions are on screen. When a runway is made slippery by liquid water, ICAO requires that the state promulgate this fact. The state will do so by promulgating its minimum friction coefficient for successful braking. Obviously, slippery when wet implies the braking coefficient of friction is below this level. In addition, ICAO recommends that the coverage and depth of water is assessed and promulgated as one of 4 categories. When the runway is discoloured by the moisture, but the depth of water is deemed insignificant, it is described as damp. A wet runway does, however, have a significant depth of water, but there is no pooling to form puddles. A runway with water patches has pooling, but it is not extensive. Which leaves us with flooded, which, as you can imagine, is when the runway is pretty much covered in pools of water. Our final topic in this section is braking action. That is, the frictional coefficient of brake tire and runway surface. This frictional coefficient can be assessed in a number of ways, some perhaps more technical than others. Various meters like the Tapley, Mu or Skidometer are less subjective and less fun than racing a Land Rover down the centre of the runway, standing on the brakes and seeing what happens. The friction coefficient is measured to 2 significant figures and promulgated in accordance with the table here, which also shows the descriptor and ICAO code. Promulgation is mainly by SNOTAM, which was examined under Aeronautical Information Services. This brings to a conclusion our examination of runway contamination and braking action.